Hi, this is Nick Richard with RadWave, and today I wanted to continue on from where we left off in the last video. And just to recap, in the last video, we went through the Breakthrough Listen Open Data Archive and looked at how this table was all structured. We then dug into the Open Data Archive metadata scraper, and with this, specifically, we looked at how to scrape all of the data from from the tables in that archive, then how to download just the Guppy headers to obtain the rest of the metadata for each of the files, and then how to specifically get an approximate start time for each of those files so that we could form the basis for the RadWave engine that allows us to select files that are adjacent in time. So for today, what I want to get into is how Breakthrough Listen differs from SETI at Home, and then how to plot the spectrum for these Guppy files. So SETI at Home was a distributed computing project that allowed the SETI at Home system to send tasks to users who had the client application running on their personal computers. So that way they could do the work here and send the results back to SETI at Home. This allowed SETI at Home to have a large number of client machines to help in all this automated processing. And so with this system, the SETI at Home servers are the ones that really controlled which machines were processing which data, and also the rate at which that those tasks were assigned to the individual users and how quickly they were able to get the results back. With Breakthrough Listen, we have the same basic concept that the Breakthrough Listen project hosts a whole bunch of data, and there are users who have machines that they can use to process it. The difference, however, is that in this case, the users send requests to Breakthrough Listen to obtain data, and Breakthrough Listen then has to send the results, which is a large file, to the users at the rate that they determine. And so here we can have multiple users all requesting results at the exact same time, and Breakthrough Listen having to try to satisfy all those requests at a rate determined by the users. And so in general, this isn't too big of a deal, but the problem that could come up, and I'm not sure how big a problem this may or may not be, but the problem is that there's a fixed pipe. So there's a network, an internet, that connects the Breakthrough Listen servers to the user's client machines. And if the aggregate amount of data that's being requested at one time is too big to fit through the network, what can happen is only some of these downloads will succeed and some of them won't. And so if there are a very large number of users all doing this at the same time, there's a chance that they could saturate this network connection. So with RadWave, in order to make sure that we have a way to prevent this saturation from happening, what we do here is we first have users send a request to the RadWave servers to see how many concurrent downloads are happening at the same time, like how many are currently active. And if that's below a certain threshold number, then their requests will go to the Breakthrough Listen servers so that way it can be satisfied. And the RadWave engine, we can in real time change the number of users, so we can in real time observe the the success rate of these downloads, so that way we can keep track and gain an understanding as to just how much data we can successfully transfer across to users. So that's just a small, simple thing that RadWave does internally to make sure that we can maximize the number of successful downloads that happen, and make sure that we don't overly stress the Breakthrough Listen servers by accident. So with all that being said, let's just take a moment just to look at the data that we actually scraped to really understand why I think this may be a concern. So with this validate Guppy script, we had created these and these other scripts, we had created these different CSV files. And so just this one that we got that comes straight from the Open Data Archive table, we're able to see the download link for each individual file. So each string here corresponds to a URL. And the first part of that URL is the host that's serving this particular file. And as you go through this list here, we can see that there's really not a lot of different hosts for each of these. So I made a really quick little script here to show how much data each host is serving. So we can see that there are really only 6 hosts that have all of the Guppy data from the Green Bank Telescope. And 2 of these hosts have the vast majority of it. So this BLPD5 SSL Berkeley.edu has 210 terabytes of data that it's serving to the public, and BLPD6 .ssl.berkeley.edu also has 210 terabytes of data, and the rest of these have less. So there's really only, from what I can tell, there's only 2 servers. Usually when servers are named like this, when they only differ by a single digit, usually means this is like a single physical machine. And so it's going to have, 1, maybe 2 Ethernet cables on the back of it. And that may be the real bottleneck for all the network data that it's feeding out. So if you get to the point where you saturate that at that point of that server, they really may not be able to host anymore. And with the servers named like this in particular, there's a chance that all of their network cables all feed into a small set of network switches. So actually, like those cables all go to one, and that goes to their internet service provider. And so that particular switch may be taking the aggregate of all 5 of these servers, and the Google Cloud one may be serving very little content. And so that's where we don't exactly know where the bottlenecking, or if there is a bottleneck, first of all, like maybe these are serving a way different from what I'm assuming. But what exactly the network configuration is and where the primary bottlenecks exist, and depend upon what data people download at what times, whether or not there'll be any concern at all. But regardless, I want to make sure that RadWave is acting responsibly and just has a way to keep the number of requests at a rate that can be satisfied. Okay, so with all that being said, let's take a look at what the data actually looks like. So with the RadWave Explorer, once we've created collections, we can look at their content. So with this particular collection here, we have that same TIC 159.107.668 object that we're looking at, which has a center frequency of 845 megahertz and a bandwidth of 187.5 megahertz and a duration of 22.9 seconds. And we can interactively look at the spectrogram here. So this top plot is a spectrogram. The vertical axis is time, and the horizontal axis is frequency. The lower plot here is the power spectral density. And so the vertical axis here is power, and the horizontal axis here is frequency. And we can use our mouse to just zoom into different portions of the spectrum in order to see what's going on. And so I had hinted at this in the last video, where we have channelized data that comes into the Green Bank telescope. So the Green Bank telescope has a number of channelizers when it's receiving all the data. And here we can really see what those channels look like. So we have 64 of them. So each of these spikes corresponds to the center of one channel, and the edges are where it dips down. So this is on the transition between two adjacent channels. So this spike right here in power, this is due to the local oscillator leaking into the receiver, which appears, even though it's not a very strong signal compared to the rest of the background, it's quite strong. And then what's really common in receivers is to have a filter to prevent any signals that are beyond the frequency range from leaking back in. And it's called aliasing. And so we have this filter roll off here that we're able to observe. And so you can see that there are 64 of these channels, and the way the receiver is configured is to butt them right up against each other in frequency to maximize the total bandwidth that we're looking at, while not having gaps in coverage. And so we can see that a number of these, some of them appear to have some very weak signals. But if we take a look, we can see that other frequencies here have quite a bit of content. And so today what I wanted to do is to dig into how to actually take the original data that we get from these raw Guppy files and transform it into a spectrum that we can actually analyze. And so for that, we're going to take a look at some code. So this code has been added to the same metadata scraper repository. And we're going to start off looking at the spectrum for all the channels. This is a fairly simple script where we're looking at one particular target, which is the same TIC 159.107.668 object. And we're trying to just pluck out one particular file. So one that has a center frequency of 845 megahertz, just like what we were looking at a moment ago, and a start UTC of this particular time. So this is the seconds since the Linux epoch. And then we get out just a single file and the metadata corresponding to it. What this does, it allows us to understand how exactly the data was recorded to disk and how exactly that particular file is structured, so we can yank out not just the header, but also the raw data from it. And the data is structured in a series of blocks. And we'll see in a moment, there's 128 blocks per file nominally. And we're going to read just a single one of them since they're large. Once we have one file, we'll observe a series of windows over it in order to calculate the spectrogram, in order to calculate the power spectral density with this Welch function, and then we'll plot the results. So let's take a peek. So here we see it's downloading one of 128 blocks of data. This one block is 128 megabytes, starting at this particular byte. It just takes a little bit of time for it to do this calculation. Okay. So here we can see the power spectral density. We see each of these 64 channels with these really large spikes in power, and we can see the filter roll off between each of these individual channels. With the power spectral density, we see the same basic effect here, where we have each of these little yellow lines corresponds to those channel centers. And then we can kind of see where it turns a little bit blue here. That's lower in power, where we have the filter roll off between the channels. And one of the things that you'll notice pretty quickly is that we're not seeing the same, powerful signals. We see some things here a little bit. We're not quite seeing those strong signals that we saw with RadWave right here. And the reason for that is the number of samples that you use per window is really, really important. But looking at since we have so many channels, we have 64 of them, and with the window sizes need to be quite large, doing this plotting just with standard tools becomes a little bit challenging. And so let's look at, instead of all of these files or all of these channels all at once, let's look at just one single channel, just the one channel that actually has this content here. So we'll stop this and we'll go back to our files. So if we look at plotting just a single channel, if we look at the window size, we can change what size this is. And now let's take a look to see what the content looks like. And as you can see, patience is a little bit of a virtue when it comes to this processing. Okay. So here, now that we've increased our window size, it's now 65,000 samples. Now we can start to have sufficient resolution to see these signals really start to pop out. And to really highlight this point, let's take a look at one more. Let's take a look at one more file. So this is, instead of just plotting a single window, or just see what the content looks like when we use a single window, we're going to use multiple windows, create spectrograms and power spectral density plots for all of them, and plot them all together so they're all lined up nicely. So this takes a little bit longer to generate since we're doing multiple window sizes. All right. So here we can see the original window size we used, which is 256 samples. We can see a middle point using just 1,000 samples for the window size, and we start to see this peak up, and then using 65,000 samples, we really see this content get highlighted here. And as you can see, as our window size increases, the frequency resolution and the time resolution changes a function of that. So when the window size is smallest, the frequency resolution is the biggest. So the more samples we use, the smaller a window, or I'm sorry, the more samples we use for our window, the finer our frequency resolution, and the coarser our time resolution. And so we can really see that highlighted when we look at the spectrogram plot. So here you can see when we're using 65,000 samples, we only get four instances of looking at this data because we only had 4 times that many samples to process with our spectrogram. With 1,000 samples, we have a much finer resolution in time, but less fine resolution and frequency. And finally, with 256, we have fairly coarse frequency resolution, but an extremely fine time resolution. But let's zoom in here to see what this content looks like. And with this particular view, it can be hard to see where exactly the signal is located. There you go. Okay. So here on this top plot, we see one frequency bin of data and many time bins here. Whereas on the bottom plot, we see 4 of these time bins, and we can, but the frequency resolution is much finer. And you can see that it's just much more difficult to tell that there's any content in this frequency bin, or especially this frequency bin, compared to the others. And that's because all of the energy that's in this particular time bin or time frequency window here is placed inside this portion of the spectrum here. And because there's so much noise on the sides, it all gets smeared into here and averaged all together. And so this one very fine spectral tone, combined with all of the noise around it, just really isn't enough to be able to see it that well. And that's especially true here, where if we were to look down, look at this entire range of frequencies, there's so much noise in the background that it really just averages out overall. And you're left with a really small peak. And that's just averaging up all of this content here. There's just so much noise becomes burdensome. So this kind of illustrates just how important it is to have frequency resolution and potentially the time resolution. If the signal only exists for a short period of time, you'd want to use a coarse frequency resolution and a fine time resolution in order to see a signal that's very short in time, or potentially very broad in frequency. Whereas when we're looking for spectral tones, then they're going to stay on the air for much longer. So we don't need as fine a time resolution, but we do need a fine frequency resolution. Okay, so that's all I had for today. I just want to encourage anyone who's interested in looking at this data in more detail, feel free to go to radwave.com, check out the call for alpha testers. We have tutorials here available, and then alpha releases as well. So anyone's welcome to to become an alpha tester, all you have to do is subscribe to the blog to have access to this page. And then you can download the RadWave engine and RadWave Explorer and get started. We're also on Discord, so feel free to join that and let me know if there's anything I can help you with, any questions I can answer. All right, talk to you next time.